Question 1. Cost-benefit analysis shows that a proposed wind farm's projected revenue is significantly higher if the wind resource mapping analysis selectively omits data from a specific, less windy season, thereby increasing the estimated annual energy production. As a certified wind energy professional CWEP, what is the most ethically and professionally responsible course of action? Option A. Focus the cost-benefit analysis solely on the most favorable wind resource data, while acknowledging in a footnote that other data was collected but deemed less relevant for the initial economic projection. Option B. Present the wind resource mapping and analysis based on all collected data, including the less windy season, and clearly communicate the implications of this comprehensive data set on the project's cost-benefit analysis, even if it reduces the projected revenue. Option C. Recommend a higher turbine hub height and more advanced turbine technology to compensate for the lower wind speeds identified in the less windy season, without altering the core wind resource mapping data. Option D. Adjust the wind resource mapping analysis to exclude data from the less windy season, as this will present a more favorable cost-benefit scenario for the project developer and expedite project approval. Correct answer is B. Present the wind resource mapping and analysis based on all collected data, including the less windy season, and clearly communicate the implications of this comprehensive data set on the project's cost-benefit analysis, even if it reduces the projected revenue. Explanation. This scenario presents a professional challenge because it pits the immediate financial interests of a project developer against the long-term integrity of wind resource assessment, which is foundational to the economic viability and environmental impact of a wind energy project. The CWEP professional is tasked with ensuring that the wind resource mapping and analysis are not only technically sound, but also ethically conducted, adhering to the principles of accuracy and transparency. The pressure to present a favorable outcome for the developer, potentially through selective data interpretation or omission, creates an ethical dilemma that requires a robust understanding of professional standards and regulatory expectations. The correct approach involves prioritizing the integrity of the wind resource assessment by presenting the most accurate and representative data, even if it leads to a less favorable initial cost-benefit analysis for the developer. This approach aligns with the core ethical obligations of a CWEP professional to uphold the accuracy and reliability of their work. Regulatory frameworks for wind energy, such as those overseen by the U.S. Department of Energy and relevant state-level environmental agencies, emphasize the importance of data integrity in project planning and permitting. Ethically, a professional must act with due diligence and avoid misrepresentation, presenting a comprehensive analysis that includes all relevant data, even if it suggests a higher initial investment or lower immediate return, ensures that future operational decisions and financial projections are based on a realistic understanding of the wind resource. This fosters long-term project sustainability and builds trust with stakeholders. An incorrect approach would be to manipulate the wind resource mapping or analysis to artificially inflate the projected energy yield or minimize perceived risks. For instance, selectively excluding periods of lower wind speeds or overemphasizing favorable data points without proper justification would constitute a misrepresentation of the resource. This violates the ethical duty of honesty and accuracy. Such actions could lead to regulatory noncompliance if the misrepresented data is used in permit applications or environmental impact assessments. Furthermore, it undermines the credibility of the CWEP professional and the wind energy industry as a whole. Another incorrect approach would be to present a highly optimistic scenario based on theoretical maximums rather than observed data, failing to account for real-world variability and uncertainty. This also misleads stakeholders and can result in projects that underperform financially and technically, potentially leading to project failure and reputational damage. A professional decision-making process in such situations should involve a clear adherence to established professional codes of conduct and regulatory requirements. A CWEP professional should first ensure they have a thorough understanding of the project's objectives and the applicable regulatory landscape. When faced with conflicting pressures, the professional must prioritize data integrity and objective analysis. If the developer insists on a biased interpretation, the professional should clearly articulate the ethical and professional implications of such a request, referencing relevant standards and regulations. If the pressure persists, the professional may need to consider withdrawing from the project to maintain their ethical standing and professional integrity. The ultimate goal is to provide an assessment that is technically sound, ethically defensible, and supports the long-term success of the wind energy project based on realistic expectations. Question 2. Regulatory review indicates that a certified wind energy professional CWEP is tasked with evaluating the performance of a wind turbine using blade element momentum (BEM) theory. The turbine's actual power output consistently deviates from the theoretical power curve generated by the BEM model under specific wind conditions. Which approach best reflects the professional and regulatory responsibilities of the CWEP in this situation? Option A. Attribute all discrepancies solely to potential sensor malfunctions, without performing a comprehensive analysis of other contributing factors to the observed performance differences. Option B. Conduct a detailed investigation into the assumptions of BEM theory and compare them against the actual site conditions and turbine operational data to identify potential sources of discrepancy, considering factors beyond the idealized BEM model. Option C. Disregard the observed deviations as inherent noise in operational data and proceed with the theoretical BEM power curve for all performance assessments. Option D. Immediately recalibrate the BEM model's input parameters until the theoretical power output precisely matches the measured power output, assuming the model itself is the sole source of error. The correct answer is B. Conduct a detailed investigation into the assumptions of BEM theory and compare them against the actual site conditions and turbine operational data to identify potential sources of discrepancy, considering factors beyond the idealized BEM model. Explanation. Scenario analysis. This scenario presents a professional challenge in assessing the performance of a wind turbine under varying atmospheric conditions. The core difficulty lies in accurately applying theoretical models like blade element momentum (BEM) theory to real-world operational data, especially when that data might be influenced by factors not explicitly accounted for in the simplified theoretical framework. A CWEP must exercise careful judgment to reconcile theoretical predictions with observed performance, ensuring that any discrepancies are understood and addressed appropriately, without compromising safety or regulatory compliance. Risk lies in misinterpreting performance data, leading to incorrect operational adjustments, maintenance decisions, or even inaccurate reporting, all of which can have significant financial and safety implications. Correct approach analysis. The correct approach involves a thorough review of the BEM theory's assumptions and limitations in the context of the specific turbine and site conditions. This includes understanding how factors like atmospheric turbulence, wind shear, tower shadow, and blade degradation can deviate from the idealized conditions assumed by BEM. The CWEP should then compare the theoretical power output predicted by BEM with the actual measured power output, investigating any significant deviations. This investigation should focus on identifying potential causes for the discrepancies, such as sensor inaccuracies, control system responses, or environmental factors that are not perfectly modeled. The regulatory justification stems from the CWEP duty to ensure the safe and efficient operation of wind energy facilities, which requires an accurate understanding of turbine performance. Adhering to industry best practices, which often involve validating theoretical models with empirical data, and understanding the limitations of those models, is implicitly required by the professional standards expected of a CWEP. Incorrect approaches analysis. One incorrect approach is to solely rely on the raw BEM theoretical output without considering real-world operational data. This fails to acknowledge that BEM is a simplified model and does not capture all the complexities of actual wind turbine operation. Regulatory and ethical failure here is a lack of due diligence in performance assessment, potentially leading to misinformed decisions that could impact turbine longevity, energy production, and grid stability. Another incorrect approach is to dismiss any deviation between BEM theory and actual performance as solely due to sensor error without a systematic investigation. While sensor error is a possibility, it is not the only or necessarily the primary cause of discrepancies. This approach prematurely closes off avenues of investigation and could overlook critical issues with the turbine's aerodynamic performance, control system, or structural integrity. The ethical failure lies in an incomplete and potentially biased assessment, which could lead to overlooking significant operational problems. A third incorrect approach is to adjust the BEM model parameters arbitrarily to match the observed data without a clear theoretical or physical justification. This is essentially curve fitting and does not represent a genuine understanding of the turbine's performance. It undermines the integrity of the theoretical model and can lead to a false sense of confidence in the model's predictive capabilities. The regulatory failure is in presenting a potentially misleading analysis of turbine performance, which could be relied upon for critical operational or investment decisions. Professional reasoning. When faced with discrepancies between theoretical models and observed performance, a CWEP should adopt a systematic, evidence-based approach. This involves 1. Understanding the theoretical model's assumptions and limitations. 2. Collecting and validating all relevant operational data. 3. Performing a comparative analysis quantifying deviations. 4. Investigating potential causes for deviation, considering both model limitations and operational factors. 5. Documenting all findings and justifications for any conclusions drawn. This process ensures that assessments are robust, transparent, and aligned with professional responsibilities to operate wind energy facilities safely and efficiently. Question 3. Consider a scenario where a wind energy developer is planning a new project and needs to select anemometers and wind vanes for the initial wind resource assessment. The project is located in a jurisdiction with specific regulations governing the accuracy, calibration, and certification of meteorological instruments used for wind energy projects. The developer has received proposals from several suppliers offering a range of instruments with varying specifications and price points. Which of the following approaches best aligns with the professional and regulatory obligations for this wind resource assessment? Option A. Utilize anemometers and wind vanes that have been previously used on other wind projects, provided they are still functioning, without verifying their current calibration status or specific regulatory compliance for this jurisdiction. Option B. Select anemometers and wind vanes that have current, traceable calibration certificates from an accredited laboratory and are certified by a recognized national or international standards body for wind energy applications, ensuring they meet the specific accuracy and reliability requirements stipulated by the local regulatory framework. Option C. Prioritize anemometers and wind vanes with the highest reported measurement range, even if their certification and calibration status are unclear or do not explicitly align with the specific requirements of the local wind energy regulations. Option D. Choose the most cost-effective anemometers and wind vanes that appear to meet general meteorological measurement standards, assuming they will be sufficiently accurate for the project's initial assessment. The correct answer is B. Select anemometers and wind vanes that have current, traceable calibration certificates from an accredited laboratory and are certified by a recognized national or international standards body for wind energy applications, ensuring they meet the specific accuracy and reliability requirements stipulated by the local regulatory framework. Explanation. This scenario presents a professional challenge due to the critical role of accurate wind resource assessment in the economic viability and operational efficiency of a wind energy project. The selection and deployment of anemometers and wind vanes are foundational to this assessment. Professional judgment is required to ensure that the chosen instrumentation not only meets technical specifications, but also complies with the stringent regulatory framework governing wind energy projects in the specified jurisdiction. Failure to adhere to these standards can lead to inaccurate data, flawed project design, regulatory noncompliance, and ultimately, significant financial and operational repercussions. The correct approach involves selecting anemometers and wind vanes that are certified and calibrated according to the standards mandated by the relevant regulatory body for wind energy projects. This ensures data integrity and compliance. Specifically, the chosen instruments must meet the accuracy, reliability, and traceability requirements outlined in the governing regulations. This approach is correct because it directly addresses the regulatory mandate for accurate and reliable wind data collection, which is a cornerstone of responsible wind energy development. Adherence to these standards minimizes the risk of data misinterpretation, ensures that the project meets performance expectations, and satisfies legal and contractual obligations. An incorrect approach would be to select anemometers and wind vanes based solely on cost or perceived ease of installation, without verifying their compliance with regulatory certification and calibration requirements. This is professionally unacceptable because it disregards the fundamental regulatory obligation to use validated instrumentation. Such a choice risks generating inaccurate wind speed and direction data, which can lead to miscalculations in energy production estimates, incorrect turbine selection, and suboptimal site layout. This directly violates the principles of due diligence and professional responsibility, potentially resulting in significant financial losses and regulatory penalties. Another incorrect approach is to rely on manufacturer claims of accuracy without independent verification or certification that aligns with the specific regulatory framework. While manufacturers provide specifications, regulatory bodies often require independent certification or adherence to specific testing protocols to ensure that instruments perform reliably under site-specific conditions and meet established industry standards. Ignoring this verification step is a failure to meet the due diligence required by the regulations, as it bypasses a critical quality assurance step designed to protect the integrity of the wind resource assessment. A third incorrect approach would be to use older, uncalibrated instruments that may have been previously used for other purposes, even if they appear functional. This is professionally unsound because wind resource assessment for a new project demands the highest level of accuracy and reliability. Older instruments may have degraded performance, and without current calibration traceable to recognized standards, their data cannot be trusted. This directly contravenes the regulatory emphasis on using current, calibrated, and appropriate instrumentation for critical data collection, leading to unreliable assessments and potential project failure. The professional decision-making process for similar situations should involve a systematic review of the project's regulatory requirements, followed by an assessment of available instrumentation against those requirements. This includes verifying manufacturer specifications, seeking independent certifications where mandated, and ensuring that calibration procedures and records meet regulatory standards. A risk-based approach should be employed, prioritizing instruments that offer the highest degree of confidence in data accuracy and regulatory compliance, even if they represent a higher initial investment. Question 4. The efficiency study reveals that a newly commissioned wind farm is consistently underperforming compared to the predictions made during the wind resource assessment phase. As a certified wind energy professional, CWEP, which of the following approaches best addresses this situation to ensure professional integrity and accurate future planning? Option A. Immediately focus on potential equipment failures or operational issues as the primary cause of the underperformance, assuming the wind resource assessment was accurate. Option B. Conclude that the underperformance is within acceptable statistical margins of error for wind resource assessments, and no further investigation is immediately required. Option C. Reevaluate the site's wind resource based on the actual operational data, disregarding the original assessment's methodologies and assumptions. Option D. Conduct a thorough review of the entire wind resource assessment process, from data acquisition and quality control to the selection of modeling techniques and uncertainty analysis, to identify any potential methodological flaws or data biases. The correct answer is D. Conduct a thorough review of the entire wind resource assessment process, from data acquisition and quality control to the selection of modeling techniques and uncertainty analysis, to identify any potential methodological flaws or data biases. Explanation. The efficiency study reveals a discrepancy between predicted and actual wind turbine performance at a newly commissioned site. This scenario is professionally challenging because it directly impacts the financial viability of the wind farm and the credibility of the assessment process. The certified wind energy professional, CWEP, must meticulously evaluate the wind resource assessment, raw methodology to identify the root cause of the underperformance, ensuring adherence to established best practices and regulatory expectations. The correct approach involves a comprehensive review of the entire WRA process, from data collection and site selection to modeling and uncertainty analysis. This includes scrutinizing the quality and representativeness of meteorological data, the appropriateness of the chosen modeling software and techniques, and the thoroughness of the uncertainty quantification. This approach is correct because it aligns with the fundamental principles of professional responsibility and due diligence expected of a CWEP. It seeks to identify systemic issues rather than superficial explanations, thereby ensuring that corrective actions are effective and that future assessments are more reliable. Regulatory frameworks, such as those governing renewable energy project development and investment, implicitly or explicitly require that assessments be conducted with a high degree of accuracy and transparency, and that any deviations from expected performance are thoroughly investigated. Ethical considerations also demand that professionals act in the best interest of stakeholders by providing accurate and unbiased assessments. An incorrect approach would be to immediately attribute the underperformance to a single, easily identifiable factor without a systematic investigation. For instance, solely blaming equipment malfunction without first verifying the accuracy of the wind resource data used in the initial predictions represents a failure of due diligence. This approach is ethically flawed as it may lead to incorrect conclusions and misallocation of resources for remediation. It also fails to meet the professional standard of thoroughness. Another incorrect approach would be to dismiss the discrepancy as within acceptable statistical variation, without a rigorous reevaluation of the underlying assumptions and data. This is problematic because it abdicates the professional responsibility to investigate significant deviations and could lead to continued underperformance and financial losses for investors, violating the principle of acting with competence and care. Professionals should approach such situations by first establishing a clear understanding of the WRA process and its critical control points. They should then systematically work through each stage of the assessment, comparing the actual site conditions and performance against the documented WRA methodology and findings. This structured, evidence-based approach, coupled with a commitment to transparency and accuracy, is essential for making sound professional judgments and upholding the integrity of the wind energy industry. Question 5. The investigation demonstrates that a proposed wind farm site exhibits significant variations in wind speed measurements between two meteorological masts located at different elevations on a complex terrain. The CWEP must determine the most appropriate method to characterize the wind shear across the turbine rotor swept area for the final site assessment report. Option A. Manually adjust the wind speed data from the higher mast to match the lower mast readings, assuming the lower mast is more representative. Option B. Employ a simple linear extrapolation of wind speed from the ground level to the hub height based on the data from the mast with the highest recorded wind speed. Option C. Rely solely on the average wind speed from the two masts, assuming a uniform wind profile across the entire site. Option D. Utilize a validated wind modeling software that incorporates terrain effects and atmospheric stability to interpolate and extrapolate wind data across the rotor diameter. Correct answer is D. Utilize a validated wind modeling software that incorporates terrain effects and atmospheric stability to interpolate and extrapolate wind data across the rotor diameter. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a certified wind energy professional, CWEP, to interpret complex wind behavior data in the context of regulatory compliance and operational efficiency. The challenge lies in discerning the most accurate and defensible method for characterizing wind shear, a critical parameter for turbine performance and structural integrity, when faced with potentially conflicting data sources or interpretations. Misinterpreting wind shear can lead to suboptimal turbine siting, inaccurate energy production forecasts, and potentially unsafe operating conditions, all of which have significant financial and regulatory implications. The professional must exercise sound judgment, relying on established methodologies and regulatory guidance to make informed decisions. Correct approach analysis. The correct approach involves utilizing a validated, industry-standard wind modeling software that incorporates established meteorological principles and is demonstrably capable of accurately interpolating and extrapolating wind speed data across the turbine rotor swept area, considering terrain effects and atmospheric stability. This approach is correct because it aligns with the principles of good engineering practice and the implicit requirements of regulatory frameworks that mandate accurate site assessment for wind energy projects. Such software typically incorporates algorithms that are peer-reviewed and validated against empirical data, providing a robust and defensible basis for wind shear calculations. Adhering to these established methodologies ensures that the wind resource assessment is reliable, supports accurate energy yield predictions, and meets the due diligence expected of a CWEP. Incorrect approach is analysis. An incorrect approach would be to solely rely on raw, unvalidated data from a limited number of meteorological masts without applying advanced modeling techniques. This fails to account for the spatial variability of wind within the rotor diameter and the influence of complex terrain, leading to an incomplete and potentially inaccurate representation of wind shear. It also bypasses the established best practices for wind resource assessment, which are implicitly or explicitly supported by regulatory guidance promoting robust data analysis. Another incorrect approach would be to arbitrarily adjust raw data to fit a desired energy production outcome. This is ethically unsound and constitutes a violation of professional integrity. Regulatory bodies expect objective and unbiased assessments. Such manipulation undermines the credibility of the entire project and can lead to severe regulatory penalties and legal repercussions. A further incorrect approach would be to use a simplified, linear extrapolation of wind speed from ground level to the hub height without considering atmospheric stability or turbulence. While seemingly straightforward, this method ignores the complex physics of wind flow and can lead to significant under- or overestimation of wind shear, impacting turbine performance and potentially leading to structural fatigue or operational issues, which would be contrary to the safety and efficiency standards expected by regulatory oversight. Professional reasoning. In situations involving wind characteristic analysis, a CWEP should adopt a systematic and evidence-based approach. First, identify all available data sources and their limitations. Second, select appropriate, validated tools and methodologies that are recognized within the wind energy industry and align with regulatory expectations for accuracy and reliability. Third, critically evaluate the results, comparing them against theoretical expectations and any available empirical data. Finally, document the entire process thoroughly, including the rationale for methodology selection and any assumptions made, to ensure transparency and defensibility. This structured decision-making process, grounded in scientific principles and professional ethics, is crucial for navigating the complexities of wind resource assessment and ensuring compliance with all applicable regulations. Question 6. The analysis reveals that a wind turbine is experiencing increased vibration levels during operation. Considering the fundamental aerodynamic principles of lift, drag, and angle of attack, which operational adjustment strategy is most aligned with a professional understanding of these forces and their impact on turbine performance and stability within the context of the Certified Wind Energy Professional CWEP framework? Option A. Increasing the rotor speed to overcome the vibration. Option B. Initiating a full system shutdown and waiting for the next scheduled maintenance. Option C. Adjusting the blade pitch to reduce the angle of attack. Option D. Applying a temporary lubricant to the gearbox to dampen vibrations. The correct answer is C. Adjusting the blade pitch to reduce the angle of attack. Explanation. This scenario is professionally challenging because it requires a wind energy professional to interpret complex aerodynamic principles, lift, drag, angle of attack, within the specific regulatory framework of the Certified Wind Energy Professional (CWEP) exam. Challenge lies in applying theoretical knowledge to practical operational decisions, while adhering strictly to the CWEP-defined scope and any implied or explicit regulatory guidance relevant to wind turbine performance and safety, without resorting to external or generalized standards. The professional must demonstrate an understanding of how these aerodynamic forces influence turbine behavior and how operational adjustments, informed by this understanding, align with best practices as defined by the CWEP. The correct approach involves recognizing that operational adjustments to mitigate excessive vibration, which is often a symptom of suboptimal aerodynamic performance, must be grounded in an understanding of how changes in the angle of attack directly affect the lift and drag experienced by the rotor blades. Specifically, a reduction in the angle of attack generally decreases both lift and drag, which can reduce the forces contributing to vibration. This approach is correct because it directly addresses the physical phenomena influencing turbine operation and aligns with the practical application of aerodynamic principles expected of a CWEP. The CWEP framework, by its nature, emphasizes practical competence in wind energy systems and understanding how to manage aerodynamic forces for optimal and safe operation is a core competency. This approach demonstrates a professional's ability to diagnose and propose solutions based on fundamental engineering principles relevant to wind turbine function. An incorrect approach would be to suggest operational adjustments based solely on visual cues of vibration, without considering the underlying aerodynamic causes. This fails because it bypasses the critical step of diagnosing the root cause, which is essential for effective and safe turbine management. It also risks implementing ineffective or even detrimental adjustments. Another incorrect approach would be to recommend adjustments based on generalized maintenance schedules or manufacturer recommendations that do not specifically address the observed aerodynamic performance issues. While manufacturer guidelines are important, they may not cover every unique operational scenario or performance anomaly. Relying on them without a deeper understanding of the aerodynamic principles at play in this specific situation represents a failure to apply specialized knowledge. A further incorrect approach would be to propose adjustments based on anecdotal evidence from other wind farms without verifying their applicability to the specific turbine model and site conditions. This ignores the unique aerodynamic characteristics of different turbine designs and site-specific environmental factors, which are crucial for accurate diagnosis and effective intervention. The professional decision-making process for similar situations should involve a systematic approach. First, observe and document the symptoms, e.g., vibration levels. Second, apply fundamental engineering principles, such as aerodynamics. Hypothesize the root cause. Third, consider the specific operational context and regulatory framework, in this case, the CWEP scope. Fourth, propose targeted adjustments based on the hypothesized cause and relevant principles. Finally, monitor the results and iterate as necessary. This structured approach ensures that decisions are informed, evidence-based, and aligned with professional standards. Question 7. System analysis indicates a consistent, albeit minor, deviation in the blade pitch angle readings from nominal operational parameters across multiple turbines at a wind farm. The deviation is not causing immediate alarm conditions or tripping the turbines offline, but it is outside the manufacturer's specified tolerance for optimal performance. As a certified wind energy professional, CWEP, operating under U.S. regulatory frameworks, what is the most appropriate immediate course of action? Option A. Manually adjust the pitch control set points on the affected turbines to bring the readings back within the manufacturer's specified tolerance, assuming the deviation is a minor calibration drift. Option B. Immediately halt operations of all affected turbines to prevent potential damage, without further investigation into the specific cause of the pitch deviation. Option C. Initiate a comprehensive diagnostic sequence for the pitch control system on the affected turbines, cross-referencing findings with the turbine operation and maintenance manual and relevant OSHA safety guidelines for maintenance procedures. Option D. Continue normal operation and monitor the deviation, assuming it is within acceptable operational limits for extended periods and will self-correct. The correct answer is C. Initiate a comprehensive diagnostic sequence for the pitch control system on the affected turbines, cross-referencing findings with the turbine operation and maintenance manual and relevant OSHA safety guidelines for maintenance procedures. Explanation: this scenario presents a professional challenge because it requires a wind energy professional to balance operational efficiency with regulatory compliance and safety protocols when faced with an anomaly in blade pitch control. The core of the challenge lies in interpreting sensor data, understanding the implications of pitch control deviations, and selecting an appropriate response that adheres to the Certified Wind Energy Professional (CWEP) standards and any applicable U.S. federal or state regulations governing wind turbine operation and maintenance. The professional must avoid making assumptions and instead rely on established procedures and regulatory guidance. The correct approach involves a systematic investigation of the pitch control anomaly, prioritizing safety and regulatory adherence. This means initiating a diagnostic procedure to pinpoint the root cause of the deviation, which could range from a faulty sensor to a more complex control system issue. The professional must then consult the turbine's operation and maintenance manual, as well as relevant U.S. regulatory guidelines, e.g., those from OSHA for worker safety, or NERC standards if applicable to grid interconnection and reliability, though CWEP focuses on the turbine itself and its immediate operational environment. This approach ensures that any corrective actions are informed, documented, and compliant, minimizing risks to personnel, equipment, and the grid. An incorrect approach would be to immediately adjust the pitch control settings without a thorough diagnosis. This bypasses the established diagnostic protocols and could mask a more serious underlying problem, potentially leading to catastrophic failure or unsafe operating conditions. Such an action would violate the professional duty of care and could contraindicate specific operational guidelines or manufacturer recommendations, which are often implicitly or explicitly tied to regulatory compliance for safe operation. Another incorrect approach is to ignore the anomaly, assuming it is within acceptable operational tolerances or will resolve itself. This demonstrates a failure to proactively manage potential risks and could lead to equipment damage, reduced energy production, or safety hazards. Regulatory frameworks often mandate reporting and addressing operational anomalies, and ignoring such issues can result in non-compliance and potential penalties. A third incorrect approach is to rely solely on anecdotal experience or the advice of less qualified personnel without consulting official documentation or regulatory guidance. While experience is valuable, it must be grounded in established procedures and regulatory requirements. Deviating from these without proper justification or authorization is a significant professional failing and can lead to non-compliance and unsafe practices. The professional decision-making process for similar situations should involve a structured approach. 1. Recognize and document the anomaly. 2. Consult relevant documentation, manuals, logs. 3. Identify potential causes based on available data. 4. Initiate diagnostic procedures. 5. Consult regulatory requirements and safety protocols. 6. Implement corrective actions based on diagnosis and compliance. 7. Document all actions and outcomes. This systematic process ensures that decisions are data-driven, compliant, and prioritize safety and operational integrity. Question 8. To address the challenge of optimizing turbine placement while ensuring compliance with U.S. federal and state environmental regulations and mitigating local community concerns, which micrositing strategy demonstrates the most responsible and professional approach for a certified wind energy professional? Option A. Implement micrositing changes based on the least expensive foundation and access road construction, assuming that regulatory hurdles and community objections can be addressed through reactive measures once the primary design is established. Option B. Conduct a comprehensive environmental impact assessment, consult with relevant U.S. federal and state agencies, and engage local stakeholders early and continuously to inform micrositing decisions that balance energy generation with regulatory compliance and community acceptance. Option C. Prioritize micrositing adjustments that maximize energy production based on wind resource data, with secondary consideration for potential environmental impacts and community feedback only if they become significant obstacles. Option D. Rely on generic industry best practices for micrositing without specific verification against the unique environmental sensitivities and local zoning ordinances of the project site, assuming these practices are universally applicable and sufficient. The correct answer is C. Prioritize micrositing adjustments that maximize energy production based on wind resource data, with secondary consideration for potential environmental impacts and community feedback only if they become significant obstacles. Explanation. The scenario presents a professional challenge because micrositing decisions for wind turbines directly impact project viability, environmental compliance, and community relations. Balancing optimal energy production with potential negative externalities requires careful consideration of multiple factors, including regulatory requirements, stakeholder concerns, and technical feasibility. The Certified Wind Energy Professional (CWEP) designation implies a commitment to upholding professional standards and adhering to the specific regulatory framework governing wind energy projects in the relevant jurisdiction. The correct approach involves a comprehensive assessment that prioritizes regulatory compliance and stakeholder engagement. This means thoroughly investigating potential impacts on protected species, aviation, radar, and noise levels, ensuring all proposed micrositing adjustments meet or exceed the standards set by the relevant U.S. federal and state environmental protection agencies, aviation authorities, and local zoning ordinances. Furthermore, proactively engaging with local communities and landowners to address concerns and incorporate feedback into the micrositing process is crucial for obtaining social license and avoiding protracted disputes. This approach aligns with ethical professional conduct by demonstrating due diligence, transparency, and a commitment to responsible development. An incorrect approach would be to solely focus on maximizing energy yield, without adequately considering regulatory constraints or community impacts. For instance, prioritizing a turbine location that offers the highest wind speeds but encroaches on a known migratory bird path without conducting a thorough environmental impact assessment, and obtaining necessary permits from the U.S. Fish and Wildlife Service would be a significant regulatory failure. Similarly, disregarding local noise ordinances or visual impact concerns raised by residents, leading to potential legal challenges and project delays, represents a failure in stakeholder management and adherence to local regulations. Another incorrect approach would be to rely on outdated or incomplete site data, leading to micrositing decisions that fail to account for unforeseen environmental or logistical challenges, potentially violating best practice guidelines and leading to operational inefficiencies or safety hazards. Professionals should employ a decision-making framework that begins with a thorough understanding of the applicable regulatory landscape, including federal, state, and local laws and guidelines. This should be followed by a detailed site assessment that considers all relevant technical, environmental, and social factors. Stakeholder consultation should be an ongoing process, integrated from the initial stages of micrositing through to operational phases. Finally, all decisions must be documented, with clear justification based on data, regulatory requirements, and stakeholder input, ensuring accountability and transparency. Question 9. The review process indicates a potential discrepancy between the documented specifications for a wind turbine's gearbox and the actual installed component. As a certified wind energy professional, CWEP, what is the most appropriate immediate action to address this situation? Option A. Initiate a physical inspection and cross-reference the gearbox's serial number and any visible model information with the original purchase orders and installation records to verify the correct specifications. Option B. Assume the documentation is accurate and proceed with ongoing operational monitoring based on the provided specifications. Option C. Rely solely on a visual inspection of the gearbox's external appearance to confirm its model and specification. Option D. Adjust operational parameters based on the documented specifications to optimize performance, pending a later review. The correct answer is A. Initiate a physical inspection and cross-reference the gearbox's serial number and any visible model information with the original purchase orders and installation records to verify the correct specifications. Explanation. The review process indicates a potential discrepancy in the documentation for a critical wind turbine component, specifically the gearbox. This scenario is professionally challenging because it directly impacts the operational integrity, safety, and long-term performance of the wind turbine. Misrepresenting or overlooking critical component specifications can lead to premature failure, costly repairs, safety hazards for personnel, and potential regulatory noncompliance. Careful judgment is required to ensure all documentation accurately reflects the installed components and adheres to the manufacturer's specifications and relevant industry standards. Correct approach involves a thorough investigation to verify the actual installed gearbox model against the documented specifications. This includes cross-referencing serial numbers, inspecting physical labels on the component, and reviewing original purchase orders and installation records. This approach is right because it prioritizes factual accuracy and adherence to the manufacturer's approved specifications, which are foundational to safe and efficient operation. It aligns with the professional responsibility of a certified wind energy professional, CWEP, to ensure that all aspects of a wind turbine's installation and maintenance are documented accurately and comply with the operational parameters defined by the component manufacturer. This upholds the integrity of the asset and ensures compliance with any warranty or performance guarantees. An incorrect approach would be to assume the documentation is correct without verification. This fails to uphold the professional duty of due diligence and can lead to operating the turbine outside its design parameters, potentially causing damage or safety risks. Another incorrect approach would be to rely solely on visual inspection without cross-referencing with official records. While visual inspection is important, it may not reveal subtle differences in specifications that are critical for performance and longevity. A third incorrect approach would be to proceed with operational adjustments based on the potentially erroneous documentation, without first confirming the actual component specifications. This directly contravenes the principle of operating within defined safety and performance limits and could lead to significant operational failures and safety incidents. Professionals should adopt a systematic approach to resolving such discrepancies. This involves 1. Identifying the discrepancy and its potential impact. 2. Initiating a verification process using multiple data sources, physical inspection, serial numbers, purchase orders, installation logs. 3. Documenting all findings meticulously. 4. If a discrepancy is confirmed, initiating the appropriate corrective actions, which may include updating documentation, consulting with the manufacturer, or performing further inspections. This structured decision-making process ensures that actions are based on verified facts and adhere to professional standards and regulatory requirements. Question 10. What factors determine the selection and deployment of wind measurement equipment for a new wind farm development to ensure compliance with industry, best practices, and regulatory frameworks governing wind resource assessment? Option A. The adherence of the equipment to recognized industry standards for accuracy, calibration, and data integrity, as well as its suitability for the specific site conditions and project objectives. Option B. Cost-effectiveness of the equipment, prioritizing lower initial investment over long-term data accuracy and reliability. Option C. The availability of equipment that can provide immediate data, regardless of its certification status or calibration history. Option D. The preference of the project developer for a particular brand of equipment, irrespective of its technical specifications or compliance with regulatory requirements. Correct answer is C. The availability of equipment that can provide immediate data, regardless of its certification status or calibration history. Explanation. This scenario presents a professional challenge because it requires a certified wind energy professional, CWEP, to balance the immediate need for project data with the long-term integrity of wind resource assessment. The ethical dilemma arises from potential pressure to compromise measurement standards for expediency, which could lead to inaccurate energy yield predictions and subsequent financial and operational misjudgments. Careful judgment is required to uphold professional standards and regulatory compliance. The correct approach involves prioritizing the use of calibrated and certified anemometers that meet industry standards and regulatory requirements for wind resource assessment. This ensures the accuracy and reliability of the collected wind speed data, which is fundamental for predicting the energy output of a wind farm. Adhering to these standards, as often stipulated by regulatory bodies and best practice guidelines within the wind energy sector, is crucial for transparent and defensible project development. It aligns with the professional obligation to provide accurate information and avoid misleading stakeholders. An incorrect approach would be to proceed with uncalibrated or non-certified equipment, even if it appears functional. This failure directly contravenes the principles of accurate data collection and professional integrity. Such an action could lead to significant under- or overestimation of energy production, impacting financial viability, grid connection agreements, and investor confidence. Ethically, it constitutes a misrepresentation of the project's potential. Another incorrect approach is to rely solely on historical data from a different site, without verifying its applicability or accounting for local microclimate variations. While historical data can be a starting point, wind resource assessment demands site-specific measurements. Ignoring this requirement, even for speed, risks generating a flawed energy yield assessment, which is a direct violation of the professional duty to conduct thorough and site-specific evaluations. Finally, an incorrect approach would be to accept data from a sensor that has a known intermittent fault without proper documentation and correction. This introduces uncertainty and potential bias into the dataset. Professional responsibility dictates that all data anomalies are identified, investigated, and addressed appropriately, either by correcting the data or by excluding it with clear justification, rather than implicitly accepting potentially erroneous readings. The professional decision-making process for similar situations should involve a systematic evaluation of measurement protocols against established industry standards and regulatory mandates. Professionals must proactively identify potential risks to data integrity, such as equipment calibration status or data anomalies. When faced with pressure or expediency, the decision-maker should always refer back to the core principles of accurate data collection, ethical conduct, and regulatory compliance. If there is any doubt about the validity or representativeness of the data, the professional should advocate for the necessary steps to ensure accuracy, even if it causes delays. This includes seeking clarification from supervisors or regulatory bodies if necessary. Question 11. Governance review demonstrates that a wind farm developer is pushing for the expedited commissioning of a new turbine, citing tight project deadlines. They have identified minor surface imperfections on the turbine blades, which they believe are cosmetic and will not significantly affect aerodynamic performance. As a certified wind energy professional, CWEP, overseeing the commissioning process, what is the most appropriate course of action regarding these blade surface imperfections? Option A. Advocate for a detailed aerodynamic assessment of the blades to quantify the impact of the imperfections on performance and structural integrity before commissioning. Option B. Recommend immediate blade replacement to ensure optimal performance and avoid any potential future issues. Option C. Advise the developer that the decision regarding blade imperfections is solely theirs to make, and the CWEP role is limited to observation. Option D. Accept the developer's assessment that the imperfections are minor and proceed with commissioning to meet project deadlines. Correct answer is A. Advocate for a detailed aerodynamic assessment of the blades to quantify the impact of the imperfections on performance and structural integrity before commissioning. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a CWEP to balance the immediate economic pressures of a project developer with the long-term operational integrity and safety dictated by aerodynamic principles and regulatory compliance. Developers desire to expedite a project by overlooking potential aerodynamic performance degradation due to unaddressed blade surface imperfections, creates a conflict between short-term cost savings and adherence to established engineering standards, and potential regulatory requirements for performance verification and maintenance. A CWEP must exercise sound professional judgment to ensure that decisions are grounded in technical merit and regulatory adherence, not solely on commercial expediency. Correct approach analysis. The correct approach involves advocating for a thorough aerodynamic assessment of the turbine blades, specifically focusing on the impact of surface imperfections on performance and structural integrity. This aligns with the professional responsibility of a CWEP to ensure the safe, efficient, and reliable operation of wind energy assets. While the CWEP exam is jurisdiction agnostic in its core principles, the underlying expectation is adherence to best practices in wind energy engineering, which implicitly includes following relevant national or regional standards for turbine design, operation, and maintenance. Such standards often mandate performance monitoring and require addressing deviations that could compromise safety or efficiency. Therefore, recommending a detailed assessment is the most responsible action, as it directly addresses the potential aerodynamic consequences and informs necessary corrective actions to maintain compliance with operational standards and potentially regulatory performance benchmarks. Incorrect approach is analysis. One incorrect approach is to accept the developer's assertion that the imperfections are minor and will not significantly impact performance without independent verification. This fails to uphold the professional duty of due diligence and technical rigor. It risks overlooking subtle but critical aerodynamic effects that could lead to reduced energy yield, increased fatigue loads, and premature component failure, potentially violating operational performance guarantees or maintenance requirements stipulated by regulatory bodies or contractual agreements. Another incorrect approach is to immediately recommend blade replacement without a proper assessment. While blade replacement might be the ultimate solution, it is an economically significant decision. Proceeding without a detailed aerodynamic analysis is premature and potentially wasteful. It bypasses the professional responsibility to provide evidence-based recommendations and could lead to unnecessary expenditure, failing to demonstrate cost-effectiveness and sound engineering judgment. A third incorrect approach is to defer the decision entirely to the developer, assuming they have the ultimate authority. While developers are the project owners, CWEP have a professional obligation to provide expert advice based on technical and safety considerations. Abdicating this responsibility is a failure to act in accordance with professional standards and could have serious consequences for the project's long-term viability and safety. Professional reasoning. Professionals facing similar situations should employ a structured decision-making process. First, clearly identify the technical issue, blade surface imperfections, and its potential aerodynamic consequences. Second, consult relevant industry best practices and any applicable jurisdictional guidelines or standards for wind turbine operation and maintenance. Third, assess the potential risks and benefits of different courses of action, considering technical performance, safety, environmental impact, and economic factors. Fourth, communicate findings and recommendations clearly and objectively to stakeholders, providing a technical rationale for each recommendation. Finally, document all assessments, recommendations, and decisions to ensure accountability and provide a record for future reference. Question 12. The control framework reveals that a new wind turbine project is being designed for a site with moderate wind speeds and a sensitive nearby residential area. The engineering team is evaluating several airfoil profiles, each with distinct aerodynamic characteristics. Which approach best aligns with the professional responsibilities of a certified wind energy professional operating under U.S. regulatory guidelines? Option A. Select the airfoil profile that demonstrates the highest theoretical power coefficient across a broad range of wind speeds, as maximizing energy capture is the primary objective. Option B. Opt for the airfoil profile that offers the lowest manufacturing cost, assuming that any performance or noise differences will be negligible in the long term. Option C. Prioritize an airfoil profile that is commonly used in similar wind regimes, without conducting a detailed analysis of its specific performance or noise characteristics for this particular project. Option D. Choose an airfoil profile that has a proven track record of low noise emissions and good performance at the expected operational wind speeds, while also considering its suitability for the specific site conditions and potential regulatory compliance issues related to noise. The correct answer is A. Select the airfoil profile that demonstrates the highest theoretical power coefficient across a broad range of wind speeds, as maximizing energy capture is the primary objective. Explanation. This scenario presents a professional challenge because the selection of an airfoil profile for a new wind turbine design involves balancing competing performance objectives and adhering to specific regulatory requirements that may not be immediately obvious or explicitly stated in general industry best practices. The Certified Wind Energy Professional (CWEP) designation implies a responsibility to operate within the established regulatory framework, which in this context would be the U.S. regulatory framework governing wind energy development and operation. A critical aspect of this is ensuring that design choices align with safety, efficiency, and environmental standards, which are often underpinned by specific regulations. The correct approach involves a comprehensive evaluation of airfoil performance characteristics against the specific operational environment and design goals, while also cross-referencing these with applicable U.S. regulations. This means not just selecting an airfoil that offers the highest theoretical power output, but one that also demonstrates robustness, low noise emissions, and suitability for the anticipated wind conditions, all within the bounds of what is permitted and encouraged by U.S. wind energy regulations. For instance, regulations might indirectly influence airfoil selection by setting standards for noise levels or by incentivizing designs that minimize environmental impact. A CWEP must demonstrate an understanding of how these regulatory considerations translate into practical design choices. An incorrect approach would be to prioritize a single performance metric, such as maximum power coefficient, without considering the broader regulatory implications. For example, selecting an airfoil known for high tip speed ratios that might lead to excessive noise levels could violate noise abatement regulations or local ordinances, even if it offers superior energy capture. Another failure would be to rely solely on manufacturer-provided data without independent verification or consideration of how that data aligns with the specific site conditions and regulatory expectations. This could lead to a design that underperforms in real-world conditions or fails to meet compliance standards. Furthermore, ignoring potential fatigue life implications of certain airfoil designs, which could be indirectly addressed by structural integrity regulations, would also be a professional failing. Professional decision-making in such situations requires a systematic process. First, clearly define the project's performance objectives and constraints. Second, identify all relevant U.S. regulations and guidelines pertaining to wind turbine design, operation, noise, and environmental impact. Third, conduct a comparative analysis of candidate airfoil profiles, evaluating their aerodynamic performance, structural characteristics, noise generation potential, and suitability for the expected wind regime. Fourth, integrate the regulatory requirements into the evaluation criteria, prioritizing airfoils that meet or exceed these standards. Finally, document the rationale for the chosen airfoil, demonstrating how it satisfies both performance goals and regulatory mandates. Question 13. Strategic planning requires a wind energy project developer to select the most appropriate generator technology for a new 100 MW wind farm to be sited in a region with a mature and complex electricity grid in the United States. The developer must consider not only the technical performance and cost-effectiveness of different generator types, but also their ability to meet current and anticipated U.S. grid codes and reliability standards. Which of the following approaches best aligns with the regulatory framework and professional responsibilities of a certified wind energy professional CWEP in this context? Option A. Opt for the generator technology that is most commonly used in older wind farm installations within the U.S., based on the assumption that its established performance characteristics will satisfy existing grid requirements without extensive further analysis. Option B. Select a generator technology that inherently offers robust voltage and frequency regulation capabilities, can demonstrate compliance with NERC reliability standards, and has a proven track record of meeting stringent grid interconnection requirements in similar U.S. grid environments, even if it involves a higher initial investment. Option C. Prioritize the generator technology with the lowest initial capital expenditure, assuming that any necessary grid integration enhancements can be addressed through standard power conversion systems and post-installation upgrades if required by the grid operator. Option D. Choose a generator technology that maximizes energy capture under a wide range of wind speeds, with the understanding that grid integration challenges can be resolved through generic inverter solutions that are widely available and adaptable to various generator types. Correct answer is C. Prioritize the generator technology with the lowest initial capital expenditure, assuming that any necessary grid integration enhancements can be addressed through standard power conversion systems and post-installation upgrades if required by the grid operator. Explanation. This scenario presents a professional challenge because the selection of a generator type for a new wind farm has significant long-term implications for operational efficiency, grid integration, maintenance costs, and compliance with evolving grid codes. A CWEP must balance technical performance with regulatory requirements and economic viability. The challenge lies in understanding the nuanced differences between generator types and how these differences interact with the specific grid conditions and regulatory landscape of the United States. The correct approach involves a thorough evaluation of each generator type's suitability for the specific project site and grid connection requirements, prioritizing compliance with U.S. federal and state regulations, as well as relevant industry standards like those from NERC and IEEE. This includes assessing how each generator type inherently contributes to grid stability, fault ride-through capabilities, and reactive power control, all of which are critical for meeting grid operator requirements and ensuring reliable power delivery. The regulatory framework in the U.S., particularly concerning grid interconnection and operational reliability, mandates that new generation assets must demonstrate their ability to meet stringent performance criteria. Therefore, selecting a generator that inherently possesses or can be readily configured to meet these requirements, such as a synchronous generator with its inherent voltage regulation capabilities, or a permanent magnet synchronous generator, PMSG, with advanced power electronics for grid support, is paramount. This proactive approach minimizes the risk of costly retrofits or operational restrictions later. An incorrect approach would be to prioritize solely on initial capital cost, without a comprehensive assessment of long-term operational and regulatory compliance costs. For instance, selecting an induction generator solely because of its lower upfront cost might lead to significant challenges in meeting modern grid codes that require dynamic voltage and frequency support, potentially necessitating expensive external compensation equipment and limiting the farm's ability to participate in ancillary services markets. This fails to adhere to the spirit and letter of regulations that aim to ensure grid stability and reliability. Another incorrect approach would be to assume that all generator types offer equivalent grid integration capabilities. Induction generators, particularly squirrel cage types, have inherent limitations in providing fast-acting voltage and frequency control compared to synchronous or PMSG. Relying on this assumption without verifying specific grid code compliance for the chosen technology would be a significant regulatory failure, as grid operators have the authority to reject interconnection applications or impose strict operating limitations if the proposed generation does not meet their technical requirements. A third incorrect approach would be to overlook the specific requirements of the local grid operator and state-level utility regulations. While federal regulations set a baseline, regional and state authorities often have additional, more specific requirements for generator performance, such as specific fault ride-through durations or reactive power injection capabilities. Failing to investigate and comply with these granular requirements, even if a generator type is generally acceptable under broader federal guidelines, would constitute a regulatory failure and could jeopardize the project's approval and operational success. Professionals should adopt a decision-making framework that begins with a detailed understanding of the project's technical specifications, site conditions, and crucially, the applicable U.S. federal, state, and local grid interconnection standards and operational requirements. This should be followed by a comparative analysis of generator types, evaluating their technical merits against these regulatory mandates, as well as their long-term operational costs and potential for future grid service participation. Engaging early with grid operators and regulatory bodies to clarify expectations and ensure alignment is a critical step in mitigating risks and ensuring a compliant and successful project. Question 14. Risk assessment procedures indicate that the selection of LiDAR or SODAR technology for an offshore wind farm's environmental impact assessment must consider potential impacts arising from the assessment technology itself. Which of the following approaches best aligns with the regulatory framework for conducting such assessments? Option A. Prioritize LiDAR or SODAR systems with a proven low operational noise signature and minimal visual disturbance characteristics, supported by independent verification where available. Option B. Select the LiDAR or SODAR technology with the lowest upfront purchase price, assuming that data acquisition is the primary objective. Option C. Choose the LiDAR or SODAR system that offers the highest theoretical data resolution, irrespective of its operational noise or visual footprint. Option D. Deploy the LiDAR or SODAR technology that has been most widely used in previous onshore wind farm assessments, without specific consideration for offshore environmental conditions. The correct answer is A. Prioritize LiDAR or SODAR systems with a proven low operational noise signature and minimal visual disturbance characteristics, supported by independent verification where available. Explanation. The scenario presents a professional challenge in selecting the most appropriate LiDAR or SODAR technology for a wind energy project's impact assessment, specifically concerning environmental noise and visual impact. The challenge lies in balancing the need for accurate data collection with the potential for the assessment technology itself to introduce or exacerbate impacts, requiring a nuanced understanding of both the technology's capabilities and the relevant regulatory framework. Careful judgment is required to ensure the assessment is both effective and compliant. The correct approach involves selecting LiDAR or SODAR technology that has undergone independent verification for minimal operational noise emissions and has a proven track record of low visual impact in similar environments. This is justified by the regulatory requirement to conduct impact assessments that are themselves free from undue environmental disturbance. Specifically, under the framework governing wind energy projects, any assessment methodology must adhere to principles of environmental stewardship and minimize the introduction of new environmental stressors. This aligns with the overarching goal of responsible development and the avoidance of cumulative impacts. An incorrect approach would be to prioritize solely on the lowest initial cost of the LiDAR or SODAR equipment without considering its operational noise profile. This fails to meet regulatory expectations for a comprehensive and responsible impact assessment, as it risks the assessment process itself contributing to noise pollution, potentially impacting sensitive receptors and violating noise regulations. Another incorrect approach would be to select a LiDAR or SODAR system based solely on its advertised data accuracy, without investigating its visual profile or potential for light reflection. This overlooks the regulatory requirement to assess and mitigate visual impacts, which are a significant consideration for wind energy projects. The assessment technology should not introduce new or amplified visual disturbances that could negatively affect the aesthetic landscape or local communities. A further incorrect approach would be to deploy LiDAR or SODAR technology without consulting local planning authorities or environmental agencies regarding their specific guidelines or concerns about such assessment tools. This demonstrates a failure to engage with stakeholders and adhere to the spirit of collaborative environmental assessment, potentially leading to regulatory noncompliance or the need for costly reassessment if the chosen technology is deemed unsuitable post-deployment. Professionals should employ a decision-making framework that begins with a thorough review of project-specific environmental sensitivities and regulatory requirements. This should be followed by a comparative analysis of available LiDAR and SODAR technologies, focusing on their documented operational noise levels, visual impact characteristics, and any independent certifications or case studies demonstrating their suitability for sensitive environments. Consultation with regulatory bodies and environmental specialists should be an integral part of this process to ensure the chosen technology aligns with all applicable standards and best practices for impact assessment. Question 15. The assessment process reveals that a wind turbine's aerodynamic performance analysis indicates a slight but consistent underperformance compared to the manufacturer's predicted power curve. The project manager, concerned about potential delays in project financing if this underperformance is highlighted, asks the wind energy professional to adjust the analysis to align with the predicted curve, suggesting that minor variations are typical and should be smoothed over for reporting purposes. What is the most ethically and professionally sound course of action for the wind energy professional? Option A. Inform the project manager of the ethical implications of altering the data and proceed with reporting the accurate, analyzed performance data, offering to conduct further investigation into the causes of the underperformance. Option B. Adjust the analysis to match the manufacturer's predicted power curve, attributing any discrepancies to minor, unquantifiable environmental factors and omitting specific details of the adjustment in the report. Option C. Ignore the minor discrepancies in the analysis and report the performance as predicted, assuming that the project manager's assessment of typical variations is correct. Option D. Report the actual analyzed performance data, clearly documenting any deviations from the predicted power curve and providing a detailed explanation of the methodology used, including any assumptions made. The correct answer is D. Report the actual analyzed performance data, clearly documenting any deviations from the predicted power curve and providing a detailed explanation of the methodology used, including any assumptions made. Explanation. The assessment process reveals a common ethical dilemma in aerodynamic performance analysis, where a project manager pressures a wind energy professional to overlook minor discrepancies in performance data to meet project deadlines. This scenario is professionally challenging because it pits the professional's duty to provide accurate and reliable data against commercial pressures and the desire to maintain positive working relationships. The professional must navigate this conflict while upholding the integrity of their work and adhering to professional standards. The correct approach involves transparently reporting all findings, including any deviations from expected performance, and clearly documenting the methodology used for analysis. This upholds the professional's ethical obligation to accuracy and honesty, as mandated by professional codes of conduct that emphasize integrity and objectivity. It ensures that stakeholders have a true understanding of the wind turbine's performance, enabling informed decision-making regarding project viability and future operations. This aligns with the principles of responsible engineering and the pursuit of reliable energy generation. An incorrect approach would be to manipulate or selectively present data to obscure minor performance shortfalls. This constitutes a breach of professional ethics by misrepresenting facts and undermining the credibility of the analysis. Such actions can lead to significant financial repercussions for investors, inaccurate operational strategies, and damage to the professional's reputation and the reputation of the wind energy industry. It violates the fundamental principle of providing truthful and unbiased information. Another incorrect approach is to simply ignore the discrepancies without further investigation or reporting. This demonstrates a lack of diligence and professional responsibility. While it might avoid immediate conflict, it fails to address potential underlying issues with the turbine or the data collection process, which could have long-term consequences. It also neglects the professional's duty to inform stakeholders of all relevant performance characteristics. A third incorrect approach is to attribute the discrepancies solely to external factors without robust evidence or proper documentation. While external factors can influence performance, a professional must rigorously investigate and quantify their impact. Making unsubstantiated claims to justify performance deviations is a form of data misrepresentation and erodes trust. The professional decision-making process in such situations should involve 1. A thorough understanding of the professional code of conduct and ethical guidelines. 2. A commitment to data integrity and objective analysis. 3. Clear and open communication with all relevant parties, presenting findings factually and without embellishment. 4. Documenting all assumptions, methodologies, and results meticulously. 5. Seeking guidance from senior colleagues or professional bodies if faced with undue pressure. Question 16. Market research demonstrates that advanced computational fluid dynamics, CFD, simulations can potentially offer more granular insights into micro-siting optimization for wind turbines, leading to improved energy capture. A project team proposes using a novel, highly complex CFD model for a critical wind farm development project, claiming it will significantly outperform standard industry practices. What is the most professionally responsible approach for a certified wind energy professional, CWEP, to take regarding the integration of these advanced CFD results into the project's final design and energy yield assessment? Option A. Defer to the project developer's preference for the advanced CFD model, prioritizing their desire for potentially higher energy yield predictions over rigorous verification. Option B. Conduct a thorough validation of the advanced CFD model's outputs against empirical data from similar sites or established, simpler models, and document all assumptions and limitations before integrating the results into critical project decisions. Option C. Immediately incorporate the advanced CFD results into the project design and energy yield assessment, as the potential for improved performance justifies the use of cutting-edge technology. Option D. Rely solely on the CFD simulation, providers' assurances of the model's accuracy and sophistication, assuming that their proprietary algorithms are inherently superior to existing methods. The correct answer is C. Immediately incorporate the advanced CFD results into the project design and energy yield assessment, as the potential for improved performance justifies the use of cutting-edge technology. Explanation. This scenario is professionally challenging because it requires a wind energy professional to balance the pursuit of technological advancement and potential performance gains with the imperative of adhering to established regulatory frameworks and ensuring the integrity of data used for critical decision-making. The Certified Wind Energy Professional, CWEP, designation implies a commitment to professional standards that prioritize accuracy, reliability, and compliance. Misinterpreting or misapplying CFD results can lead to suboptimal turbine siting, inaccurate energy yield predictions, and potentially non-compliance with environmental or grid connection regulations, all of which have significant financial and operational consequences. The correct approach involves a thorough validation of CFD model outputs against empirical data and established industry best practices before integrating them into critical project decisions. This aligns with the CWEP ethical obligation to provide competent and reliable professional services. Regulatory frameworks, while not explicitly detailed here as per the prompt's constraint to avoid specific jurisdiction unless provided, generally mandate that professional opinions and recommendations be based on sound engineering principles and verifiable data. The CWEP certification implicitly requires adherence to such principles, ensuring that any advanced modeling techniques are rigorously tested and proven to be accurate and reliable within the operational context. This approach upholds professional integrity and minimizes risks associated with unverified technological assumptions. An incorrect approach would be to blindly accept CFD simulation results without independent verification, especially if they deviate significantly from expected performance or established models. This failure to validate could lead to decisions based on flawed data, potentially violating regulatory requirements for accurate energy production forecasting or environmental impact assessments. Another incorrect approach is to prioritize the novelty or perceived sophistication of the CFD methodology over its proven accuracy and applicability to the specific site conditions and turbine technology. This can result in the adoption of tools or techniques that are not robust enough for real-world application, leading to unreliable outcomes and a breach of professional duty. Furthermore, neglecting to document the validation process and the assumptions made during the CFD modeling can hinder transparency and accountability, which are often implicitly or explicitly required by professional standards and regulatory oversight. Professionals should employ a decision-making framework that emphasizes a phased approach to adopting new technologies or methodologies. This framework should include 1. Understanding the problem and the potential benefits of the proposed solution, e.g., advanced CFD for improved site assessment. 2. Thoroughly researching and evaluating the proposed methodology, including its theoretical underpinnings and limitations. 3. Conducting rigorous validation of the methodology against known data or simpler, proven models. 4. Assessing the regulatory and ethical implications of its application. And 5. Making a well-informed decision based on a comprehensive risk-benefit analysis, prioritizing accuracy, reliability, and compliance. Question 17. The assessment process reveals that a wind farm's operational data indicates a consistent pattern of higher than anticipated flapwise bending moments on the rotor blades during specific wind speed ranges, potentially impacting long-term fatigue life. Which of the following represents the most professionally responsible and regulatory compliant course of action? Option A. Classify the observed load deviations as within acceptable operational tolerances based on general industry experience, and continue monitoring without a specific, data-driven investigation. Option B. Conduct a series of visual inspections of the rotor blades to identify any visible signs of damage or wear that might correlate with the observed load patterns. Option C. Initiate a detailed analysis of the operational load data, comparing it against the turbine manufacturer's design specifications and relevant national wind turbine structural integrity standards to determine the extent of potential fatigue damage and inform appropriate mitigation strategies. Option D. Adjust the turbine's control parameters to reduce power output during the identified wind speed ranges, assuming this will inherently mitigate any fatigue concerns without further investigation. The correct answer is C. Initiate a detailed analysis of the operational load data, comparing it against the turbine manufacturer's design specifications and relevant national wind turbine structural integrity standards to determine the extent of potential fatigue damage and inform appropriate mitigation strategies. Explanation. The assessment process reveals a critical juncture in the operational phase of a wind farm, specifically concerning the long-term integrity of turbine rotors. Understanding and mitigating rotor loads and fatigue is paramount for ensuring both the economic viability and safety of the wind energy project. This scenario is professionally challenging because it requires a nuanced understanding of complex aerodynamic and structural interactions, coupled with a rigorous adherence to established industry standards and regulatory requirements to prevent catastrophic failures and ensure sustainable energy generation. The decision-making process must balance operational efficiency with long-term asset management and public safety. The correct approach involves a comprehensive review of the turbine's operational data against the manufacturer's specifications and relevant national standards for wind turbine structural integrity and fatigue assessment. This includes analyzing historical load data, comparing it against design assumptions, and evaluating the effectiveness of implemented load mitigation strategies. The justification for this approach lies in its proactive and data-driven nature, directly addressing the potential for fatigue damage. It aligns with the principles of responsible asset management and the regulatory obligation to operate wind turbines safely and reliably, as mandated by frameworks such as the IEC 61400 series of standards, which are foundational for wind turbine design and operation in many jurisdictions, including those that inform the CWEP certification. These standards provide the technical basis for assessing fatigue life and ensuring that operational practices do not exceed design limits. An incorrect approach would be to solely rely on visual inspections without correlating findings with operational load data. This is professionally unacceptable because visual inspections, while important, cannot quantify the cumulative fatigue damage caused by operational loads. It fails to address the root cause of potential fatigue issues and neglects the regulatory requirement to demonstrate ongoing structural integrity based on performance monitoring. Another incorrect approach is to dismiss observed load deviations as minor anomalies without further investigation, assuming the turbine's design can inherently accommodate such variations. This is a significant ethical and regulatory failure. It demonstrates a lack of due diligence and a disregard for the potential for accelerated fatigue accumulation, which could lead to premature component failure and safety hazards. This approach ignores the principle of conservative design and the need for continuous monitoring and validation of operational performance against design parameters. Third incorrect approach would be to implement load reduction measures based on anecdotal evidence or generalized industry best practices without a specific analysis of the turbine's unique operational context and load history. While general best practices are valuable, their application must be tailored to the specific turbine and site conditions. Failing to do so may result in ineffective mitigation or, conversely, unnecessarily curtailing power generation, impacting the project's economic performance without a clear, data-supported rationale. This approach lacks the rigor required by regulatory frameworks that demand evidence-based decision-making for operational adjustments. The professional decision-making process for similar situations should follow a structured framework. 1. Data acquisition and validation. Ensure all relevant operational data, loads, environmental conditions, performance metrics, is accurately collected and validated. 2. Comparative analysis. Compare collected data against design specifications, manufacturer recommendations, and applicable industry standards, e.g., IEC 61400 series. 3. Root cause identification. Investigate any deviations or anomalies to understand their underlying causes, particularly concerning rotor loads and fatigue. 4. Risk assessment. Evaluate the potential consequences of identified issues on structural integrity, safety, and economic performance. 5. Mitigation strategy development. Design and implement appropriate mitigation measures based on data analysis and risk assessment. 6. Performance monitoring and feedback. Continuously monitor the effectiveness of implemented strategies and adjust as necessary, creating a feedback loop for ongoing asset management. Question 18. Risk assessment procedures indicate that a specific wind turbine's gearbox has shown an increasing trend in vibration anomalies over the past 6 months. What is the most appropriate next step for a certified wind energy professional CWEP to take in addressing this mechanical system risk? Option A. Conduct a detailed vibration analysis using advanced diagnostic tools. Cross-reference findings with historical maintenance logs and manufacturer recommendations, and develop a targeted maintenance plan based on the severity and potential failure modes identified. Option B. Rely on the lead technician's experience to perform a visual inspection and address any obvious external signs of wear or damage on the gearbox. Option C. Immediately schedule a full gearbox replacement to preemptively avoid any potential future failure, regardless of the current operational status or specific anomaly data. Option D. Implement a temporary operational derating of the turbine whenever vibration levels exceed a predefined threshold, without further investigation into the root cause of the anomalies. The correct answer is A. Conduct a detailed vibration analysis using advanced diagnostic tools, cross-reference findings with historical maintenance logs and manufacturer recommendations, and develop a targeted maintenance plan based on the severity and potential failure modes identified. Explanation. This scenario is professionally challenging because it requires a certified wind energy professional CWEP to balance operational efficiency with safety and regulatory compliance when identifying and mitigating risks associated with mechanical systems. The CWEP must not only understand the technical aspects of wind turbine mechanics, but also apply a systematic risk assessment methodology that aligns with the specific regulatory framework governing wind energy operations in their jurisdiction. The challenge lies in accurately identifying potential failure modes, assessing their likelihood and impact, and then proposing mitigation strategies that are both effective and compliant. The correct approach involves a comprehensive review of historical maintenance records, operational data, and manufacturer specifications to identify recurring mechanical issues or potential failure points. This data-driven approach allows for the prioritization of risks based on their probability of occurrence and potential severity of consequences, such as catastrophic failure, downtime, or safety hazards. This aligns with the principles of proactive risk management mandated by regulatory bodies that emphasize the importance of preventing incidents through diligent assessment and control measures. Ethical considerations also demand that the safety of personnel and the integrity of the asset are paramount, which is best achieved through a thorough and evidence-based risk assessment. An incorrect approach would be to rely solely on anecdotal evidence or the opinions of a few experienced technicians, without a structured data analysis. This fails to provide a robust, objective basis for risk assessment and may overlook critical but less frequently observed issues. It also deviates from the systematic approach expected by regulatory oversight, which often requires documented evidence of risk evaluation. Another incorrect approach is to focus exclusively on the most visible or frequently occurring minor issues, neglecting the potential for less frequent but more severe mechanical failures. This reactive stance prioritizes immediate, easily addressed problems over potentially catastrophic, though less common, events. This is a failure of comprehensive risk assessment, which must consider the full spectrum of potential hazards, from minor inconveniences to major safety and operational disruptions. A third incorrect approach is to implement mitigation strategies without a clear understanding of their cost-effectiveness or potential unintended consequences on other mechanical systems or operational performance. This can lead to inefficient resource allocation and may introduce new risks. Effective risk management requires a balanced consideration of mitigation feasibility, impact, and cost, all within the established regulatory and operational context. Professional reasoning in such situations requires a structured, data-informed decision-making process. This involves 1. Defining the scope of the risk assessment, 2. Systematically identifying potential mechanical failure modes, 3. Analyzing the likelihood and impact of each failure, 4. Evaluating existing controls, 5. Determining the level of risk, 6. Developing and implementing appropriate mitigation strategies, and 7. Monitoring and reviewing the effectiveness of these strategies. This process ensures that decisions are grounded in evidence, aligned with regulatory requirements, and ethically sound, prioritizing safety and operational integrity. Question 19. The audit findings indicate a potential operational efficiency improvement that involves altering the turbine's operational parameters, which may affect noise levels and bird activity. Which of the following actions is the most appropriate regulatory compliance approach for the certified wind energy professional? Option A. Conduct a thorough review of the project's environmental impact assessment (IA) and all relevant permits to determine if the proposed change necessitates a formal amendment or modification before implementation. Option B. Proceed with the change after obtaining verbal confirmation from a single environmental consultant that the alteration is unlikely to cause significant environmental harm. Option C. Immediately implement the operational change to realize the efficiency gains, assuming that minor parameter adjustments do not require further regulatory review. Option D. Implement the change and then notify the relevant regulatory bodies of the alteration, relying on their post-implementation review to address any compliance issues. Correct answer is C. Immediately implement the operational change to realize the efficiency gains, assuming that minor parameter adjustments do not require further regulatory review. Explanation. This scenario presents a professional challenge because it requires a wind energy professional to navigate a situation where a perceived operational improvement might conflict with established regulatory requirements for environmental impact assessment. The professional must exercise careful judgment to balance efficiency gains with legal and environmental obligations. The correct approach involves a thorough review of the project's existing environmental impact assessment, IA, and relevant permitting conditions before implementing any changes. This is justified by the regulatory framework governing wind energy projects, which mandates adherence to approved EIAs and permits. These documents outline specific environmental protection measures, monitoring requirements, and operational constraints designed to mitigate potential negative impacts. Deviating from these without proper regulatory approval could lead to noncompliance, fines, and reputational damage. An incorrect approach would be to proceed with the proposed operational change based solely on the perceived efficiency benefits without consulting the EIA and permits. This fails to acknowledge the legally binding nature of these documents and the potential for unforeseen environmental consequences. Such an action would violate the principle of regulatory compliance, a cornerstone of professional conduct in the wind energy sector. Another incorrect approach would be to assume that any operational change that does not directly involve physical modification of the turbine or infrastructure is exempt from EIA review. This is a flawed assumption, as operational changes can have indirect environmental impacts, such as altered noise profiles or changes in bird flight patterns, which are typically addressed within the EIA. Ignoring this possibility demonstrates a lack of due diligence and a misunderstanding of the comprehensive scope of environmental regulations. Finally, an incorrect approach would be to seek informal approval from a single regulatory agency representative without following the formal amendment or modification process. While individual interactions can be helpful, official approval for changes impacting environmental commitments typically requires a formal submission and review process to ensure all stakeholders and regulatory requirements are met. Relying on informal assurances can lead to disputes and noncompliance if the representative's understanding or authority is limited. The professional decision-making process for similar situations should involve a systematic approach. 1. Identify the proposed change and its potential implications. 2. Consult the project's approved Environmental Impact Assessment (IA) and all associated permits and licenses. 3. Determine if the proposed change falls within the scope of existing approvals or requires a formal amendment or modification. 4. If a modification is needed, initiate the appropriate regulatory process, engaging with all relevant authorities. 5. Document all communications and approvals meticulously. 6. Prioritize regulatory compliance and environmental protection over short-term operational gains. Question 20. The performance metrics show that the wind resource mapping analysis for a proposed wind farm project has been completed using a combination of publicly available meteorological data and proprietary modeling software. The analysis indicates a strong wind resource, but the specific methodologies and data validation protocols used in the proprietary software have not been explicitly documented or cross-referenced against the standards outlined in the governing regulatory framework for wind energy project permitting in the United States. Which approach best ensures regulatory compliance and professional integrity for this wind energy project? Option A. Proceed with the current analysis, assuming that the proprietary software's advanced algorithms inherently meet or exceed regulatory expectations for wind resource assessment. Option B. Conduct a supplementary analysis using a different, publicly recognized wind modeling tool and compare the results, focusing on the consistency of the overall wind speed estimates. Option C. Focus the reporting on the high-level wind speed averages, downplaying any details about the specific modeling software or data validation processes to avoid potential scrutiny. Option D. Reevaluate the wind resource mapping analysis to ensure that all data sources, modeling techniques, and uncertainty assessments strictly adhere to the methodologies and validation requirements specified by the relevant U.S. regulatory framework for wind energy projects. The correct answer is A. Proceed with the current analysis, assuming that the proprietary software's advanced algorithms inherently meet or exceed regulatory expectations for wind resource assessment. Explanation: Scenario analysis. This scenario is professionally challenging because it requires a certified wind energy professional, CWEP, to interpret wind resource mapping data in the context of specific regulatory requirements for project permitting and environmental impact assessment. The challenge lies in ensuring that the analysis not only accurately reflects the wind resource, but also adheres to the precise standards and guidelines mandated by the relevant regulatory bodies for the jurisdiction in which the project is located. Failure to align the analysis with these requirements can lead to significant delays, project rejection, or costly remediation efforts. Professionals must demonstrate a nuanced understanding of how mapping data translates into actionable insights that satisfy legal and environmental obligations. Correct approach analysis. The correct approach involves utilizing wind resource mapping data that has been generated and validated according to the specific standards and methodologies prescribed by the governing regulatory framework for the CWEP certification. This means ensuring that the data sources, interpolation techniques, and uncertainty assessments are consistent with the guidelines established by the relevant national or regional authorities responsible for wind energy development and environmental review. For instance, if the CWEP certification is tied to U.S. regulations, this would involve adhering to standards set by agencies like the Department of Energy or state-level environmental protection agencies regarding wind resource assessment for permitting. The justification for this approach is rooted in regulatory compliance and the ethical obligation to provide accurate and defensible data that supports informed decision-making by regulatory bodies and stakeholders. It ensures that the wind resource assessment is robust, transparent, and meets the legal thresholds for project approval. Incorrect approach is analysis. An incorrect approach would be to rely on wind resource mapping data that, while potentially accurate in a general sense, has not been prepared or validated according to the specific methodologies and data quality standards mandated by the relevant regulatory framework for the CWEP. This could include using proprietary software with unverified algorithms, employing data sources that are not recognized by regulatory bodies, or failing to conduct appropriate uncertainty analysis as required. Such an approach fails to meet the regulatory requirements for wind resource assessment, rendering the data insufficient for permitting purposes. Ethically, it is a failure to uphold the professional standards expected of a CWEP, as it risks misleading regulatory bodies and the public about the project's viability and potential impacts. Another incorrect approach would be to present raw, unanalyzed wind data without contextualizing it within the specific regulatory requirements for site assessment, such as failing to address micro-siting considerations or long-term variability as stipulated by the governing framework. This demonstrates a lack of understanding of how the data must be presented and interpreted to satisfy legal and environmental obligations. Professional reasoning. Professionals in this field must adopt a proactive and compliance-driven approach to wind resource mapping and analysis. The decision-making process should begin with a thorough understanding of the specific regulatory framework governing the project's jurisdiction. This involves identifying all applicable laws, guidelines, and standards related to wind resource assessment for permitting and environmental review. Before commencing any analysis, professionals should confirm that their data sources, methodologies, and validation processes align with these requirements. Regular consultation with regulatory agencies and staying updated on any changes to guidelines are crucial. When presenting findings, it is essential to clearly articulate how the analysis meets each regulatory criterion, including any assumptions made and their justifications. This ensures transparency and builds confidence with stakeholders and regulatory bodies.